The glow of hot steel cutting through the dark. There's something visceral about watching raw power take shape. Inside the facility, molten steel emerges from the furnace like a flowing ribbon of light. As it hits the rollers, intense orange heat and scattered sparks fill the air. The slab is then guided into the primary rolling mill, where it's shaped under massive pressure. The mechanical rhythm here is relentless, each beat forging structure into the steel. Cooling sprays hiss as they contact the red-hot surface, maintaining temperature uniformity and surface quality. You can almost hear the metal resisting the force. The glowing beam moves along the conveyor, its form tightening as it's compressed and flattened. This segment is key. Precision-controlled rollers adjust thickness, ensuring each coil meets strict dimensional tolerances. One by one, the coils begin to form, an elegant loop of engineering and heat. The final curve is fascinating to watch. As the steel cools from bright red to a muted orange, it curls naturally into tight rolls. The coiling tension is calibrated automatically to prevent internal stress and deformation during cooling. What starts as blazing intensity ends in calculated control. Each roll, still steaming, waits to be tested, stamped, and shipped. It's not just molten metal being shaped. It's consistency, strength, and endurance forged in every meter. When road safety depends on steel, every detail matters. This is how crash barriers are made. Each barrier begins as raw steel coil, fed into a forming line where rollers shape it into the signature W or double beam profile. The speed and force are impressive. Steel yields to precision without hesitation. Next, each beam is cut to length, holes are punched, and edges are smoothed. Dimensional tolerances are tight, because these systems must perform under extreme impact. All designs undergo real-world crash testing before approval. Watching the barrier deform, absorb energy, and hold its position, it's proof that engineering saves lives. Final products are galvanized for corrosion resistance, then stacked and sent out for installation. With 21 models produced and tested, this facility in Ostrava delivers impact-rated safety systems that protect roads across the region. Glowing billets roll into view, signaling the start of a fully automated ring forging process built for aerospace precision. A high-speed blade slices through steel with pinpoint accuracy. The ring forging process begins here. Sensors calibrate blade pressure in real time, ensuring each section matches the required diameter before it's ever heated. Sparks fly, the edge comes out clean, and the trimmed piece moves forward for forging. Before cutting, pipes are measured and positioned using servo-driven alignment tables for maximum repeatability. Glowing billets roll into view, signaling the next stage of a fully automated system built for aerospace precision. Heating stations bring steel blanks to over 1,200 degrees Celsius. Robots equipped with heat-resistant grippers swiftly load the billets onto the press line. No manual handling needed. You can feel the intensity as the red-hot metal enters the preforming press. Each billet is marked with a unique identifier to enable full traceability through the system. Here, the billet is shaped into a thick disc, using controlled high-pressure deformation. The preform is then transferred by robotic arms to a radial axial ring rolling mill. This is where the real magic happens. The material is compressed and expanded simultaneously, forming a seamless ring with precise inner and outer diameters. It's amazing to watch the glowing ring widen while retaining its integrity under extreme pressure. Rollers dynamically adjust force and position based on live feedback from torque and temperature sensors. Infrared cameras and force sensors monitor temperature and deformation in real time, making adjustments as needed. The system ensures tight tolerances and zero human error. Once rolling is complete, robotic arms remove the forged ring and transfer it to controlled cooling zones. Each movement is precise, almost mechanical, yet there's something alive in the way the system reacts instantly to variations. Post-forging, the rings are sent through automated quality control stations, including dimensional checks, ultrasonic inspection, and surface defect scanning. These checks happen without interrupting the flow, total synchronization in motion. If a ring doesn't meet spec, it's diverted for rework or flagged for investigation by quality control engineers. Finally, the cooled rings are stacked, tagged, and moved into staging, ready for final machining or shipment. Heat, pressure, and precision. This is how American Axle's metal-formed products take shape across North America. At Oxford Forge, tens of thousands of axle shafts and ring gears are produced daily using competitive tooling and forging systems. Guan Forge follows with high volume output of yokes, gears, and pinions through advanced press and die technology. At the Cheektowaga plant, differential gears for transmissions are forged, machined, heat-treated, and assembled under one roof, including induction hardening for durability. Meanwhile, 3 facilities in Ohio perform hot, warm, and cold forging to create net and near-net parts that minimize downstream machining. Melver's operation combines cross-wedge rolling and multi-station extrusion to shape drive pinions and trunnions. At MSP, forging experts develop closed die parts using proprietary techniques, while ACU Gear delivers net-shaped differential components machined and ready for assembly. Then there's Dionic, the die-making arm, providing high-speed milling, grinding, and EDM. Every detail is measured, forged, and finished with one goal: stronger, lighter, and more efficient parts. Watching this process unfold is like seeing raw force refined into engineering purpose. This is where grinding balls are born. Steel rods are heated until they glow, then transferred beneath a pneumatic hammer. With each controlled blow, the red-hot material is shaped into a perfect grinding ball. Watching the hammer slam down with such force, it's brutal and brilliant at the same time. Each mode delivers consistent power, reliable, repeatable, and built for production. The balls are then quenched in water, cooling them rapidly while locking in structural integrity. No fancy robotics here, just raw heat, human control, and serious kinetic energy. This is old-school forging with modern reliability, and it's still one of the most effective ways to produce durable grinding media. Molten steel is poured into massive electric arc furnaces, beginning the transformation into high-grade forgings. Ladle refining and vacuum degassing follow, eliminating impurities and adjusting chemistry. Watching the liquid metal glow like lava, it's impossible not to feel the heat even through the screen. Next, molten steel is cast into large ingots weighing up to 450 tons, then transferred to the open die forging press. This 12,000-ton press, paired with a 450-ton manipulator, shapes steel into rotors, shafts, and vessel components. Every impact molds structure, not just shape. Forgings undergo controlled heat treatment in 25-meter-long furnaces, followed by precision machining on multi-axis CNC machines, some handling parts up to 300 tons. Testing labs scan for flaws using ultrasonic, radiographic, and spectrometer systems. This is where quality is confirmed, not assumed. Final products, used in wind, marine, power, and nuclear industries, are prepared for global delivery. It's engineering on an epic scale, and every step reflects intensity and expertise. This is the world behind seamless pipe production. It's not just manufacturing, it's controlled transformation. It begins with raw billets heated in an annular furnace until glowing red. Then comes piercing, where a rotating mandrel transforms the solid billet into a hollow shell. It's intense, like metal being reborn under force and flame. In the pipe mill, the shell undergoes elongation and wall thinning, gradually shaped into seamless form. Tension reduction at the sizing mill ensures diameter accuracy, followed by rapid cooling to lock in the steel's properties. Sawing cuts each pipe to length, and straightening aligns them with remarkable precision. Visual inspection follows, but machines don't catch everything, so trained eyes double-check. Then, non-destructive testing scans for internal flaws. Marking comes next for traceability, and finally, the pipes are bundled and packed, ready for shipment. Behind every seamless pipe is a process built on temperature, torque, and a sharp eye for detail. This is where steel becomes a lifeline for the energy of the future. In the production of H2-ready pipes for the Wolfsburg Power Project, every meter is forged with precision and purpose. It all starts with handling massive steel coils. The strip is straightened, cleaned, and guided into an accumulator that ensures seamless feeding into the forming line. Strip preparation here isn't just setup, it's calibration for consistency. Next, preforming tools gradually bend the strip into an open pipe. Before welding, the edges are aligned with absolute care. Every alignment here speaks of the engineering behind pressure-safe gas pipelines. High-frequency induction, HFI welding, joins the seam with intense localized heat, creating a strong, uniform bond without filler material. After welding, internal and external weld beads are scraped off to ensure smooth surfaces. A weld annealing unit follows, stabilizing the joint's microstructure. Pipes then travel through dual air cooling lines, monitored by temperature sensors that guarantee the structure remains intact. The temperature has to stay within range. Too hot, and the structure warps. Too cold, and it cracks. Precision kicks in again as pipe strings are cut to length. Each section is measured, water ejected, and subjected to ultrasonic pipe end testing. This step is critical. Any flaw at this stage could compromise entire kilometers of pipe. pipes are turned for full weld inspection, ensuring no defects go undetected. Internal stamping applies traceable IDs, and cross-transfer units direct the pipes into finishing. Blasting units clean the surface, removing mill scale before plastic coating begins. Inductive heating preps the pipe. Then extrusion units apply layers of protective plastic. The cooling line hardens the coating, while inkjet markers print quality data. Ends are beveled, then labeled for assurance. Every movement is a masterclass in timing and control. As the final step, massive cranes stack the pipes onto rail cars, ready for transport to their new home, safeguarding Wolfsburg's energy future. It's not just pipe production, it's infrastructure, readiness, and trust, built one section at a time. Built for strength and speed, these railway wheel sets go through intense processes. After axle machining and wheel fitting, the assemblies are heat-treated in gas or electric furnaces with fire clay or fiber linings. Everything's PC-controlled and logged. Watching massive wheels balanced and tested for rail duty is industrial precision at its finest. There's a certain rhythm to metal removal when the tool is right. This is the Coro Mill 390 in action, a high-performance milling cutter built for precision and flexibility. The demo shows shoulder milling first. The cutter maintains a stable path, leaving behind clean 90 degrees walls. Pocketing follows, where chips curl away smoothly under consistent feed. Slotting is next. Aggressive yet controlled, with excellent chip evacuation. Face milling wraps up the sequence, producing a flat, even surface with minimal vibration. Tool deflection is barely noticeable. Watching the cutter handle each pass with confidence is genuinely satisfying. The insert geometry, edge sharpness, and tool path stability all work together to deliver repeatable results. It's not just cutting, it's engineered consistency. Aluminum isn't just carved, it's milled with intent. On this mill-step CNC machine, a blower wheel blank undergoes a precise, multi-step process. The Z-level roughing begins first, using a 6 mm flat end mill. Each vertical pass removes 0.8 mm, with lateral engagement set to 4.8 mm. At 32 mm per second, it's not about speed, it's about control. Next comes spiral finishing. A 6 mm ball nose cutter executes a simultaneous 3-axis movement. With a step over of just 0.07 mm and feed rate of 35 mm per second, this stage focuses on surface quality, producing smooth, flowing contours. The transition is quiet, almost meditative, as the machine glides over the aluminum like it's tracing air. Even tiny imperfections can't hide from this level of detail. Every curve of the impeller must match the design to ensure aerodynamic balance. In the end, what's left isn't just a part, it's a precision component shaped by math, code, and steel. This is what raw power looks like on a lathe. Using a Sandvik Capto tool holder and a Corloy CNMG 432 insert, the rough turning operation removes heavy material fast. The chip load is aggressive, but stability is locked in. You can feel the force with every pass. Paired with a YG1 coolant through drill, the setup maximizes chip control and cooling efficiency. Industrial cutting like this doesn't just shape metal, it reshapes time and output. Steel bars slide into place as roll threading begins. No chips, no waste, just pressure and precision. The bar is forced between two dies, displacing metal to form threads instead of cutting them. It's fast, efficient, and surprisingly strong. The process cold works the grain structure, increasing durability. Watching steel flow into perfect threads without material loss, it's engineering at its smartest. This massive SDM lathe handles turbine rotors and rolling mill rolls up to 20 meters long and 2.5 meters in diameter. Incredible scale. When solid aluminum transforms under intense pressure and heat, you get something extraordinary. Precision-shaped profiles made for real-world performance. The process starts with aluminum logs cut into uniform billets, then heated to around 900 degrees Fahrenheit in a billet furnace. This softens the metal without melting it. Next, the billet is pushed by a hydraulic ram through a preheated steel die, creating the desired profile in one powerful stroke. As the profile exits the extrusion press, it enters a water quench to cool at a controlled rate, locking in specific mechanical properties. A puller system guides the extrusion across the run-out table, synchronized precisely with the press. Stretching follows, realigning and stress-relieving the profile before it's saw-cut to customer-specified lengths. Each extrusion is then artificially aged in ovens to strengthen the material. Final steps include deburring via vibratory finishing and optional surface treatments. Throughout the process, infrared laser cameras monitor billet, press, and quench temperatures in real time, because even minor fluctuations can affect final quality. Watching the glowing metal stretch and solidify into perfect geometry, it's an engineering spectacle you can't look away from. Every detail matters, and they make sure it shows in every single profile. Watch raw metal transform into high-performance screw rotors with absolute precision. At the heart of this process lies cutting-edge CNC machinery, designed specifically for helical and complex rotor profiles. Each blank is mounted, aligned, and milled with micron-level accuracy. These aren't just components, they're the pulse of compressors and superchargers. Even the slightest deviation in alignment could affect system efficiency, which is why the process demands unwavering consistency. Specialized grinding follows, shaping the rotors into their final form. This includes timing screws, pump rotors, and vacuum screws, each engineered for specific pressure and flow characteristics. Each profile must match the design specs perfectly to ensure peak aerodynamic and mechanical performance. The most fascinating part? New screw profiles can be developed in just hours, thanks to adaptive manufacturing systems. Throughout production, every rotor undergoes dimensional checks and surface inspection, ensuring high performance and tight tolerances. Operators monitor tool wear and temperature in real time to maintain precision across batches. In the world of HVAC, gas compression, or fluid processing, this level of detail is non-negotiable. When machines hum this smoothly, you know you're watching serious engineering in motion. Precision starts here. Inside UCS's compressor plant, CNC machining, rotary grinding, and thermal control come together to shape screw rotors that drive reliable, energy-efficient performance. Sharp threads, mirror-like finishes, and tight tolerances. This is what it takes to machine screws for injection molding machines. The process starts with heavy bar stock mounted onto a CNC lathe. Once centered, the rough turning phase removes excess material to form the general screw profile. Next comes precision threading. Using specialized inserts, the machine cuts helical grooves with high repeatability. Even under cutting loads, the lathe maintains concentricity across the entire shaft. It's a careful balance between torque, rigidity, and tool geometry. Finishing passes refine the surface, shiny, smooth, and ready for high-friction applications. In some cases, grooves for plastic melt flow are machined with contour control, ensuring optimized flow paths inside the barrel. Throughout the process, dimensions are checked in real time to meet strict industrial specs. A well-machined screw ensures consistent plasticizing, lower wear, and longer machine life. Watching each pass cut clean with no chatter or runout is deeply satisfying. This isn't just turning steel, it's shaping a component that drives an entire injection molding system with every rotation. Steel rods take form as raw material enters the hydraulic cylinder production line. Machining, honing, and precision welding shape cylinders that handle pressures up to 700 bars. Rod diameters range from 6 to 500 millimeters, with strokes reaching 8,000 millimeters and even 22,000 millimeters through extended capabilities. It's impressive to watch metal crafted into powerful, load-bearing systems that quietly do the heavy lifting behind industrial operations. Watching this machine work is oddly captivating. The Nargasa PP200 horizontal press brake handles metal like it's clay. With 20,000 kilograms of pressing force, it bends, curves, and forms solid materials, tube, flat bar, rod, with ease. The forming speed reaches 10 millimeters per second, while return speed climbs to 35 millimeters per second, supported by a guided piston and a 27-liter hydraulic system. Swap tools in under 30 seconds. Closed shapes, 180 degrees bends, pipe flaring, or bracket fabrication. This press does it all. Whether manual or automatic, every move is clean, forceful, and measured to 0.05 millimeters accuracy. The rotary die grips with precision as the punch descends. Sheet metal bends cleanly along the pivoting inserts, forming a crisp angle without cracks or distortion. It's a short moment, but it captures the power of mechanical leverage perfectly. When metalworking demands flexibility, The MX700 hydraulic punching machine steps in. This isn't just one press doing one job. It's a full suite of tooling operations in one rugged frame. It starts with punch setup. Operators insert the die and screw it in place, then mount the punch into the nut and secure it. Using manual mode, the piston is brought down and the die holder lifted until both components align. The lower limit is adjusted so the punch enters the die by exactly 2 millimeters. No more, no less. Precision here isn't optional. It's essential. Even this early in the process, it's clear this machine was built by people who understand metal. No requitant. Side stops are positioned to define distance. And every 200 punches, lubrication is applied to both punch and die to extend tool life. A rule to remember: the punch diameter must always exceed the sheet thickness to avoid breakage. Depending on the operation, extraction plates may be used to minimize deformation. The upper limit switch is calibrated once the punch enters the extractor. For angles, specialized tooling gets close to the edge of profiles. The stripper die enables clean 90 degrees cuts across sheets and profiles. Independent side stops allow accurate cuts up to 150 millimeters in length. It's a small adjustment with big consequences for repeatability. You don't need a giant factory to appreciate how small details like this can transform output. Next comes folding. A 2 V-slot die allows folds on 0.5 mm to 15 mm plates, a 26 mm V for thinner stock, and 56 mm for thicker. Folding depth is regulated by the stroke height. Larger tooling supports up to 300 mm parts and plates up to 20 mm thick using dual radii, one for strength, one for finesse. It's oddly satisfying watching thick steel plates fold like sheets of paper. Pipe notching gets a massive upgrade. With dedicated tooling, users notch tubes ready for welding in just 2 steps. For vertical cuts, a specialized die processes metal sheets and handrails from 0.5 mm to 20 mm thick and up to 200 mm long. 2 supporting screws, carefully set, ensure a precise cut. That kind of cut accuracy makes post-processing a breeze. Ventilation grid punching follows. The punch and pin are brought near the die, aligned carefully, and centered. Multiple holes can be punched based on part design. For arrow shapes and hollow pipes, the upper stroke limit is adjusted to match tube size. The die is lowered close to the pipe, leaving space for flattening. Side stops ensure perfectly straight alignment. When everything locks into place, it's hard not to feel impressed by the engineering. Need to cut round bars? The round bar die handles mild steel, stainless, and other metals up to 35 mm in diameter. Fence turnstile tooling works in 2 phases: flattening and cutting the tube, then punching the hole, all based on selected punch size. With the angle cutting tool, operators make quick 90 degrees cuts. By adding 2 guides, they can also cut at 45 degrees. Additional dies let you shape rounded ends on flat bars in one stroke, even across varying lengths, widths, and hole patterns. It's more than versatility, It's manufacturing freedom. The Twink tool simultaneously cuts the end of one piece and the start of the next, supporting mass production. The MX700 can be adapted to nearly any shape using custom dies, including fence arrow tips, rounded corners, or decorative forms. You can tell this machine was designed to grow with your shop, not limit it. Its physical specs back up its performance: 350 mm neck, 160 mm piston stroke, and a 600 by 350 mm working table with a central evacuation hole. The machine operates in both manual and automatic modes. In manual, the piston only descends, useful for setup. In auto, it returns automatically after punching. A built-in counter tracks operations. Safety features include a screen lock function. When the red light is on, it can run without the screen. Otherwise, it requires full protection lowered. And when you need to swap tooling, just one nut and adapter. That's it. New dies go on in minutes. Simplicity is part of the power. For anyone serious about metal, this machine isn't just a tool, it's a partner. Watching the MX700 in action is like watching skilled hands move through decades of industrial wisdom. Each tool adds capability. Each setup expands possibility. You start to realize it's not just about punching holes, it's about making parts work. As the steel coil unrolls, the sheet glides smoothly across the cutting station. Guided rollers and tension controls keep everything aligned before slicing begins. It's strangely satisfying to watch. The precision, the control, the clean-cut edges revealing raw industrial power. When steel moves like clay, you know something powerful is happening. This is 3 mm steel undergoing metal spinning, a test of pressure, form, and control. The blank is clamped tightly onto a mandrel. As it spins at high speed, a forming tool presses into the surface, gradually shaping it without removing any material. This isn't cutting, it's plastic deformation. Friction generates heat, and every pass pushes the curve deeper. Working with steel this thick demands serious force and machine rigidity. The motion looks smooth, but what's happening beneath is anything but soft. Each contour is sculpted through pressure alone. Watching the tool trace along the surface and transform a flat disc into a finished part feels raw and precise all at once. A flat copper disc spins against a forming mandrel, slowly shaped by steady tool pressure. With each pass, the metal stretches and flows into a vase form. No cutting, no waste. The control is mesmerizing, especially as curves emerge with precision and grace. Metal spinning might look simple, but it takes real skill to guide that raw copper into something this smooth and refined. Before it becomes your go-to mug, stainless steel goes through a serious transformation. The process begins with deep drawing. Flat sheets are stretched into cup-like forms using hydraulic presses. Each blank is shaped into a uniform cylinder ready for refinement. Next comes edge trimming, where the rim is cut smooth. For double wall designs, an outer shell is added and welded seamlessly to the inner wall. Bottoms are welded in place, and the body undergoes water expansion to ensure consistent volume and shape. Polishing removes imperfections, leaving behind a smooth, reflective surface. Then comes powder coating for color and durability. Watching the mugs spin evenly through the coating line is unexpectedly satisfying. Logos are imprinted using heat transfer or laser marking. Finally, each mug is inspected, packaged, and prepared for global shipping. It's easy to overlook what goes into making something so ordinary, but every press, weld, and polish ensures that this cup lasts through years of camping trips, road journeys, and quiet mornings. A small object, but backed by a big process. Watch metal sheets evolve into finished kitchenware, completely hands-free. Deep drawing forms the initial bowl shape, applying uniform pressure to stretch the steel without thinning it excessively. Each stroke of the press must maintain consistent depth to prevent wrinkling or tearing. Edge cutting removes excess material with clean shears, preparing a smooth perimeter for the next step. Trimming machines follow with high-speed precision, shaving imperfections in milliseconds. Beading comes last, curling the rim for both safety and structural strength. The precision here isn't just mechanical, it's a vision of manufacturing efficiency. You can feel the rhythm in every press, cut, and curve. Mass production doesn't have to sacrifice finesse, and this system proves it. The Zani Motion Master 800 stamps spring seats and brackets with 800 tons of controlled force. Progressive and transfer stamping operations run with zigzag feeding for material optimization. Each stroke delivers clean, accurate shapes at high speed. Watching this press in action, you can almost feel the impact. It's not just forming metal, it's shaping performance into every component. Steel beams don't just move, they're handled with precision. This automated system uses 9 fan-yoke robots to lift, rotate, and hang I-beams for washing and coating. Mag switch grippers separate each beam, reorient it vertically, then suspend it onto hooks traveling down a monorail. After treatment, the beams return and are restacked layer by layer. It's fast, synchronized, and engineered to manage high loads without missing a beat. At La Jolla Complex, 3,000 heavy components are rebuilt yearly across 50,000 square meters. Engines, torque converters, and transmissions, restored to factory specs using robotic welding and machining. Automated systems handle disassembly and reconstruction of parts weighing up to 400 tons, ensuring consistency across high-load mining equipment. Watching a 15-ton press cylinder come back to life is no small feat. After removal from the press, it arrives at the service center in Oberhausen at 2:30 a.m. No time is wasted. Disassembly begins immediately, followed by inspection and diagnosis of each component. The wear is visible. Seals degraded, surfaces scarred, tolerances off. Regeneration kicks in, polishing, precision machining, replacement of critical parts. It's intense but necessary. This cylinder handles massive force under pressure. Three working days later, the rebuilt unit moves into reassembly. Every bolt, seal, and surface is checked again before final pressure testing. Watching a hydraulic component of this size being handled with such control is impressive. Finally, the cylinder is remounted into the press system. It locks into place like it never left. Efficiency, coordination, and experience turn what seems impossible into routine. Not all engineering happens in design offices. Sometimes it happens at 2 a.m., under overhead cranes, with tools in hand and steel under load. Steel frames don't come together by chance. They're built with purpose. In this semi-trailer factory, technicians align beams, weld each joint, and reinforce critical stress points with thick steel plates. The sparks are constant, but so is the precision. Every weld strengthens the frame, preparing it to carry tons of weight over rough roads. It's not just metalwork. It's structure, tested in heat and finished by skilled hands. Heavy steel, zero hesitation. This is robotic beam assembly in action. A robotic arm lifts a 200-kilogram steel plate like it's nothing and positions it with millimeter accuracy. Add-on parts are inserted, each guided into place by automated grippers. The system switches tools seamlessly. No delays, no guesswork. Sparks burst as tack welding begins, fusing components together at key contact points. Watching this machine handle heavy steel with such precision feels surreal. Sensors confirm alignment, while software controls timing down to the second. It's not just fast, it's consistently flawless. Every motion is calibrated for repeatability, allowing column bases to be assembled with minimal human input. Efficiency like this isn't just impressive, it's the future of structural steelwork. It starts with raw stock plates, thick, heavy, and ready to be shaped. Press forming bends the steel with powerful force, setting the foundation for each cylinder. ASME certified welders fuse the seams with precision and strength. CNC profiling then defines every contour with tight tolerances. Watching this process unfold, you can't help but respect the craftsmanship. Every spark and cut brings the cylinder closer to perfection. Steel coils are flattened, aligned, and guided into massive forming rollers. This is where spiral welded steel pipe production begins. The coils are bent at precise angles and edges aligned for sub-arc welding, forming large diameter pipes with high strength and durability used in oil, gas, and water transmission. Sub-arc welding is applied both inside and outside the seam, producing consistent weld penetration throughout the pipe. Internal and external welds are automatically inspected by ultrasonic systems. These inspection systems cover 100% of the weld area and flag any inconsistency before the pipe moves forward. Once a coil ends, plasma cutting machines segment the pipe to required lengths. Watching this much metal move in perfect rhythm feels almost unreal. Spiral conveyors and mechanical arms transfer pipes down the line. End-facing machines correct surface deviations and prep the ends for field welding. For structural reliability, each pipe end can be beveled based on project-specific welding standards. Every weld is subject to hydro tests, with high-pressure water injected inside to confirm leak-tight integrity. The hydro test phase is monitored with digital sensors, recording pressure stability over time. Radiographic systems scan for internal flaws in real time. If flaws are detected, the section is marked for repair or rejection based on strict quality protocols. Precision, scale, and control. This plant doesn't just shape steel, it engineers resilience into infrastructure. Screw conveyors may look simple, but making one is anything but. It starts with heat and steel, cutting thick discs from plate and stacking them precisely. After welding onto the shaft, the screw core takes form, but it's far from done. The assembly is placed into a curved jig, locking the discs in alignment. Then, a torch slices radial notches between each flight. One by one, they're pulled outward, stretching the spiral into a uniform pitch. It's gritty, hands-on, and extremely satisfying to watch. As the structure locks into position, a protective liquid coating is applied, either anti-corrosion oil or primer, to shield the metal from oxidation and wear. Every step reflects rugged craftsmanship. It's not fast, but it's built to last. Steel rods spin into motion as the CMPRO 1600 assembles cylindrical cages with spiral precision. Longitudinal bars are clamped, rotated, and wrapped with a variable pitch wire, then welded at every intersection. It's impressive how fast and clean the welds land in perfect alignment. With controlled spacing and automatic feed, this machine delivers consistent cages ready for reinforced concrete applications. Watching steel bend and lock into shape, it's industrial craftsmanship in action. Massive lifts require flawless planning. Using lifting slings rated up to 3,000 tons, each FPSO module, S20, P60, and P20, was hoisted with care. Balanced beams and shackles handled the load beautifully. That precision? It's what keeps operations safe. High above the Swiss hills, precision unfolds in the sky. The assembly of the Potane MDT 368 AL16 tower crane begins with securing the base frame, followed by stacking mast sections one after another. Each piece is lifted by mobile cranes and bolted in place with pinpoint accuracy. The slewing unit, counter jib, and main jib follow, balanced, tested, and aligned. Seeing a crane of this size rise piece by piece feels surreal. It's not just construction, it's vertical engineering, anchored in steel and built for commanding height. Massive cranes rise above the coastline as Lekki Deep-Sea Port takes shape. Nigeria's first deep-sea port and the largest in West Africa. With a 2.7 kilometers breakwater, 3 berths, and a container yard spanning 47 hectares, this port is built for speed and scale. Each crane handles up to 45 containers per hour. Watching it all unfold, You can feel it. This isn't just infrastructure. It's momentum for an entire region. This isn't just cable stripping, it's high-efficiency copper recovery in action. The K4521 cable stripper uses a 2.2 kilowatts motor to drive 2 pairs of rollers, designed to process cables ranging from 1 to 50 millimeters in diameter. The first roller pair grips and slices the cable from the top, using 23 circular blades across 21 input channels. The second pair reverses the action. Blades underneath cut while the upper rollers pull. For thicker cables, this setup allows dual side slicing. For thin wires, one side is cut, the other compressed by a press channel. Four top-mounted adjusters control blade pressure via spring-loaded tension, letting operators fine-tune depth without damaging the conductor. On the left side, 5 extra utility blades support flexible or rubber-coated wires, designed specifically to avoid fraying or copper breakage. Flat and armored cables? No problem. Specific slots and blade combos handle each type. With built-in rollers and 2 cable holders, this machine is optimized for volume. No need for constant retooling. Each inlet is preset for common cable types. It's more than just a stripper. It's a 130-kilogram cable recycling unit capable of processing over 1.2 tons efficiently.